Well, so in the last video we proved the general Cauchy's theorem, and in this last part of the present section we are going to see the relation of conjugacy on the class of all symmetric groups Sn, and for that we are going to need the notion of partitions of a given positive integer. So let us start with that. Given any positive integer n, we say that the sequence of positive integers constitutes a partition of n if the terms of the sequence are arranged in this manner and if we add them up then we get n, that is n is their sum. So we are given a positive integer n, and for such an n a finite sequence of again positive integers where you can have any number of positive integers is said to form a partition of n if they are arranged in this manner and their sum is n. Now, a given positive integer may have many partitions. So naturally one may ask what the number of partitions of a given positive integer is, and that gives us a function. We denote by P of n the number of partitions of the positive integer n, and this function p is called the partition function. Now let's see the p values of first few positive integers. P of 1, for example, so 1 is the smallest value that n can take. This is equal to 1. Why? Because 1 equal to 1 is the only partition of 1. 1 equal to 1 I write in this sense. Here the given positive integer is 1 and the terms of the sequence, that is in this sum you have only one term which is itself 1. Such a sequence for 1 has just one term which is 1. Then P of 2 is 2, and in this case the partitions are one of them is 2 and the other is 2 equal to 1 plus 1. Well, I should not actually say that this is the partition, but rather 2 is a partition and then 1 comma 1 is a partition, because the sequences are partitions, but these equations just show that yes, their sum is 2. Then P of 3 is 3, because in this case the partitions are 3, one of them is 3 Then another one is 1 plus 2, and there is one more. 1 plus 2 means 1 comma 1 comma 1. That sequence is one partition of 3. Well, I mean 1 comma 2, and the other one is 1 comma 1 comma 1. That is equal to 3. Then P of 4. P of 4 I think is 5, yes. And in this case, the partitions are 4, 4 is equal to 4, then 4 is equal to 1 plus 3, 4 is also equal to 1 plus 1 plus 2. We are keeping this order intact. So that's why we write the smaller ones first and then increase the size. Then 4 can also be written as 2 plus 2, and finally 4 also is the sum of 4 ones. Okay, so that is P of 4. There are 1, 2, 3, 4, 5. 5 ways of partitioning 4. P of 5 is 7. So these other some higher values are just simply mentioned. You can see why it is 7. P of 6 is 11. So the first few values give us the wrong impression that P somehow, the P values increase as n increases, but the increase is very rapid, because and that you cannot see from these first few values of P. But if one somehow calculates P of 61, then that turns out to be this quite large value, 1121505. So this gives us an idea of how rapidly the P values increase with n. Now, what is the relationship between these partitions and, or rather the number of partitions and the permutations in Sn? And that relation comes like this. Every time we write a given permutation in Sn, say, as a product of disjoint cycles, which we know can always be done. We get a partition of n. We get a partition of n. But why? If sigma belongs to Sn and sigma is a product of disjoint cycles, of lengths n1, n2 and so on in R, where they have been written in this manner so that they follow these inequalities, then definitely n is their sum. N is the sum of the lengths, because if you are able to write sigma as a product of disjoint cycles whose lengths are these, then if you add them up, you are going to get n, because there are n symbols on which the permutation is acting, and those symbols have been divided into these cycles in a disjoint manner. And so this is a partition of n. So that means the moment we see a permutation in Sn and write it as a product of disjoint cycles, that thing gives us a partition of n. Now let's see one example. In S9, if we look at this particular permutation, one, 3, 2, 5, 6, 4, 7, 9, 8. 1, 3, 2, 5, 6, 4, 7, 9, 8. Then we can of course write it as a product of disjoint cycles. From the permutation sigma itself, those disjoint cycles can simply be seen and you can see that one of the cycles is a one cycle because one is kept fixed. Normally we do not write a one cycle when we write a permutation as a product of disjoint cycles, but in this case let's just write for the sake of knowing all the cycle lengths. Then 2 and 3 create a 2 cycle, a transposition. Then 4 goes to 6, 6 goes to 4, no, I think I messed it up, 4 goes to 5, 5 goes to 6 and 6 goes to 4. So they give us a 3 cycle. Seven is kept fixed, so that is a 1 cycle, and 8 and 9 give us a transposition. Thus, we get the partition. Well, when we write partition, we keep in mind this order. So we are going to get the partition created out of the cycle lengths. So we have two 1 cycles. Then we have two 2 cycles. And we have one 3 cycle of 9. Clearly, if you add them up, then you get 9. Okay. Now, if a permutation has or is a product of disjoint cycles of lengths. If a permutation means, you understand that we are in the group Sn, that is I am writing the general thing. I will come back to this S9, but let me first write something else. If a permutation is a product of disjoint cycles of lengths, these lengths where then we say that the permutation has cycle decomposition. Then the permutation is said to have the cycle decomposition this N1, N2 and so on up to Nr. Okay, so you should understand that since these are not necessarily distinct, so this is not an ordinary set. It just simply is a way of saying what the cycle lengths are in such a decomposition of a given permutation, and how many of a given length cycle there are. For example, N1 may be equal to N2, so you will get N1 and N1. Normally when we write a set, we do not repeat elements. Here however, it's a special symbol. Do not treat it as a set. For example, the above sigma in S9, that means this one has the cycle decomposition one, 2, 2, 3. The cycle decomposition only tells us the lengths of the cycles that are there in such a decomposition, but it does not tell us the actual cycles. But it gives us an idea of what the partition is that is associated with that decomposition. Okay. Now, the thing that we want to prove here is that two permutations in Sn will be conjugate if and only if they have the same cycle decomposition. That's the thing that we are now going to establish. But before that, let me just feed this some ink. It's not anything very difficult. Once we see why that is true, it will be almost obvious. It is to state this thing that we need this notion of cycle decomposition, to state this fact. We are now going to show that two permutations in Sn are conjugate if and only if they have the same cycle decomposition. It's a very nice result because normally if we are given a group, there we do not have any general such rule for deciding when two given elements are conjugate. In symmetric groups, however, this very nice thing is there. If and only if they have the same cycle decomposition. So that means what? That means this. Say you are considering any arbitrary permutation in essence, say sigma, and you also take another permutation theta in Sn, so that you can form this conjugate theta inverse sigma theta. So if you are calling this conjugate tau, then sigma and tau are conjugate, and the conjugating permutation is theta, which is giving us the conjugate. So what we are claiming here is that sigma and theta will have the same cycle decomposition, and that just simply means that when you write sigma as a product of disjoint cycles and when you write tau as a product of disjoint cycles, the cycles that you have in sigma may be quite different from the cycles that you have in tau, but those lengths that give you such a cycle decomposition, that this object, this symbol for sigma is going to be the same for what we will have for tau. And conversely also, if the permutations turn out to have the same cycle decomposition, then they will be conjugate. That is, for them such a theta will exist that will give us the conjugacy relation. So now what we are going to do, we are going to see that there is a way of knowing what theta inverse sigma theta will be if we are given theta and sigma. You may think that this is actually, are we going to calculate theta inverse sigma theta like how we normally calculate it? No, normally we know what theta inverse sigma theta is, but there is a shortcut way of calculating it. So let's see what that thing is. Let theta and sigma belong to Sn. Suppose let me write like this, okay, it will be more illuminating. Suppose sigma maps the symbol I to j, that means when your input is I, then sigma gives you the output j. But then what does theta inverse sigma theta do? Also, suppose theta takes I to some symbol s and j to some symbol t. So the symbols that we have, that we see in the action of sigma, those symbols themselves are mapped onto s and t respectively by theta. That means theta changes I to s and theta changes j to t. Then theta inverse sigma theta changes s to t. Is it true? Let us just see. Okay. Let us see like this, again using these notations. So to see if this is true, let us apply theta inverse sigma theta, this composition, in steps on S. So first, theta inverse will take s to I, because theta takes I to s, so the inverse function will do the opposite. On that I, if you then apply sigma, then you get j, and on that j, if you then further apply theta, then you get t. So that is why the composition sends s to t. So what does this tell us? It tells us that in order to calculate theta inverse sigma theta, all we have to do is we have to replace I with s and j with t. Because if you see, this is where we have our thing. This is the beginning, right? Now, if you are applying theta to these symbols, then you have the symbols changed to s and t respectively. But it turns out that that is just what theta inverse sigma theta does. So if you follow this rule and replace all the symbols appearing in sigma by their respective symbols under theta, then that will just simply give you theta inverse sigma theta. It is just as simple as that. You have sigma and you express sigma as a product of disjoint cycles. In those cycles there are some symbols. Then what you do, you look at theta and then see what theta does to each such symbol. And in place of the old symbols, you just write the new symbols. And that will be theta inverse sigma theta. And to illustrate this fact, let us take one example. For example, let's take a concrete sigma and a concrete theta. If sigma is this product of three cycles, which are disjoint of course, 5, 6, 7 and 3, 4, 2. And theta is this 1, 2, 3 times 4, 7, 4, 7. Then by this rule, theta inverse sigma theta will be what? So you look at these symbols that there are in the decomposition of sigma, and then you look at theta. What does theta do to 5? 5 does not appear in this symbol for theta, so theta does not do anything to 5, it keeps 5 fixed. So we also don't do anything to 5. Then theta also fixes 6. It does not change 6, so we also do not change 6. Theta changes 7 to 4, so this 7 is going to be replaced with 4 by us. Next, what does theta do to 3? 3 is changed to 1 by theta. So we write 1 here. 4 is changed to 7 by theta. So 7. And 2 goes to 3 under theta. So we write 3. So you can see that it's very quick. Now just to be sure that this is actually theta inverse sigma theta, let us calculate it traditionally. So if we follow our usual tradition, that is just the definition of these operations. What will be theta inverse? Theta is a product of two group. These are after all group elements. No? In permutation group, they are cycles, fine, but individually they are also permutations. So theta inverse will be the inverse of this times the inverse of this. But because these are disjoint cycles and so they commute, so we can just simply take any order, that is 1, 2, 3 inverse times 4, 7 inverse. Actually the order will be the other order, but because they commute, so we are just simply writing this, and then sigma 5, 6, 7, 3, 4, 2, and then again theta 1, 2, 3, 4, 7. So let us first write the inverses. The inverse of a cycle is obtained by taking the opposite order, the order opposite to what order these elements are following in the original cycle, that is 3, 2, 1. The inverse of a transposition is itself 3, 4, 2, 1, 2, 3, 4, 7. So let us now systematically calculate this product. Okay. What happens to 1? 1 goes to 3, then that 3 is unchanged by this, is unchanged by this, and then that 3 goes to 4 under this one. But then that 4 is unchanged by this, and this 4 goes to 7. So that means 1 ultimately goes to 7. Then what happens to 7? 7 to 4, 4 to 2, 2 to 3. So 7 to 3. Then this one takes 3 to 2. Then these two do not change 2. This one takes 2 back to 3. But then again that 3 is sent to 1 by this one, and that one is unchanged by this. So 3 goes back to 1. So we have captured 1, 7 and 3 here. Now what about 2? 2 to 1, 1 to 2. So 2 is unchanged. Then what happens to 4? This one has nothing to do with 4. 4 to 7, 7 to 5, and that's it. So 4 to 5. Then what about 5? 5 to 6, and that's it. And finally, these two do not change 6. This one sends 6 to 7, but then 7 is sent to 4 by this. So 6 goes back to 4. 1, 7, 3, 4, 5, 6. We do have 5, 6, 4 here, but if you maintain the cyclic order and write 4 first, then 4, 5, 6. And because these two cycles are disjoint, so they commute, so this is equal to this. So you see that this method actually gives us what we should get, the same thing as the traditional one. Okay, so this gives us a way of calculating the conjugates very fast, but it also shows something. Do you see what is happening I mean, what effect does this have on the cycle structure of sigma? Cycle structure of sigma means the cycle decomposition of sigma. Sigma originally is a product of 2-3 cycles. Now, all we are doing is that we are changing the individual symbols, and that change is dictated by theta. 5 and 6 are kept fixed by theta, so we have written 5 and 6. 7 is changed to 4 by theta, so we have written 4 here. So the symbols are changing, okay, changing or not changing, whatever is happening, but that has no effect on the cycle lengths. This here we had a 3 cycle, here also we have a 3 cycle, a different 3 cycle, but still a 3 cycle. Again, here also we are having a 3 cycle. In place of this one, we have another one, but still a 3 cycle. So the cycle decomposition has not changed, and this is the clue. If you have a permutation and form a conjugate like this, then the conjugate will have the same cycle decomposition as the original one, because the method just asks us to replace the symbols with some other symbols, and that has no effect on the cycle decomposition whatsoever. So that's why let us now write our conclusion. This shows that if, well, we can directly also write sigma and theta inverse sigma theta have the same cycle decomposition. And you can understand whatever we did with this example can also be done in the general case. Although we are coming to this conclusion from that example, but for a general theta and a general sigma also, the same thing will happen. You can consider the general case like this. Say sigma is a product of a finite number of some cycles of some given length. So theta will tell you what you have to do to each such cycle. You take any symbol from any cycle, see where that symbol is, where we go from that symbol, what theta is doing. Then you replace that symbol with that symbol where theta will take us from this symbol to that symbol. And you change all such symbols. That will give you theta inverse sigma theta. But the cycle decomposition does not change. The lengths stay the same. That's why we can write this final conclusion. But what about this? This is somewhat okay, it's easy. But what about the converse? If two permutations have the same cycle decomposition, then we are saying that they should also be conjugate. Can that also be seen? Yes. Conversely, consider the following permutations having the same cycle decomposition NR in Sn. So one of them is the sigma, which is this product. This is an N1 cycle, a cycle of length N1. That's why we have N1 here. Then followed by a cycle of length N2, and like that it goes. And finally, we have a cycle of length Nr, and these are disjoint cycles. Okay. This is one, and there is another such. And say tau, that is again a product of some cycle of length N1 times some cycle of length N2 and finally some cycle of length Nr. Then again from our rule we get this. Then tau is equal to theta inverse sigma theta, where shall I be able to write theta here? That is the question. Okay, let me try. A1, let me not just write these second elements. Okay, A1, A2, you understand that you have A2 here after A1, AN1, B1, BN2, X1, XNR, alpha 1, alpha N1, beta 1, beta N2, pi 1, pi Nr. So this is theta. Do you see that with this theta, if we form this conjugate, then we will get tau? Because okay, why? That's because this theta tells us that when we form theta inverse sigma theta, we have to replace each symbol of sigma by the symbol that theta is giving us. So A1 will be replaced with alpha 1, A2 will be replaced with alpha 2, which you do not see here but it's there. So you will have alpha 2 and so on, and AN1 will be replaced with alpha N1. So that will give you this cycle of tau, and similarly from the other cycles you will get the other cycles of tau. So if the cycle decomposition is the same, then we can give a conjugating permutation, the permutation that will give us the conjugate that tau is from sigma. Hence and this is the most general situation. Our claim is now established. And in fact, to illustrate this converse part, there is one example that is given here. For example, Well, I should have written the example here and then I should have written hence our claim is established, but let me just show you the example. If sigma is this permutation 1, 2, then 3, 4, 5, then 6, 7, 8, a product of a transposition and 2, 3 cycles, and tau is also another such same cycle decomposition, but the individual cycles are different. 7, 5, 1, 3, 6, 2, 4, 8. Then tau is theta inverse sigma theta, where now just like this theta you can write this concrete theta as well. It's very easy, you just write the things as they appear. 7, 5, 1, 3, 6, 2, 4, 8. And let me warn you, you do not forget that the way we have defined conjugacy, there we have the inverse first, theta inverse sigma theta. And this in fact has led to this rule that you can replace each symbol in sigma with what theta does to that symbol, and that way you get tau. It's not theta sigma theta inverse. Okay, if you write like that, then everything will change. It's not theta sigma theta inverse, but it's theta inverse sigma theta. So this way we have our claim established. Now what is the consequence of this claim? The consequence is that you are in Sn. So let us just try to see again what the claim is saying. You are in Sn and you have the conjugate classes, which you already know form a partition of Sn. So it divides Sn into disjoint compartments. Each compartment is non-empty and they are mutually disjoint. There is no common intersection and their union is Sn. So that's why they partition Sn. Well, do not confuse this partition with that partition. Okay? So our claim is saying that two permutations will belong to the same conjugate class if they have the same cycle decomposition, and conversely, if they belong to the same conjugate class, then they must have the same cycle decomposition. So that means the cycle decompositions are determining the conjugate classes, and the cycle decompositions, the number of cycle decompositions will determine how many conjugate classes there will be in Sn. And you know that number is nothing but the partition of n. Why? Because each cycle decomposition corresponds to a partition of n, and that's why the number of conjugate classes in Sn is the number of partitions of n. So this fact is written as a lemma in the text. We know precisely what permutations are conjugates to one another, and at the same time we also know the number of conjugate classes. So this is very nice, and the lemma is written like this. It is lemma 211.3. the number of conjugate classes of Sn is P of n. The number of partitions of n. So after finding out, after determining such a nice description of the conjugate classes in Sn and also their total number, we can determine how many elements, how many permutations you will find in Sn that will commute with a given permutation. Say you have some sigma in Sn, you are now in a position to say how many permutations will commute with sigma. In other words, you are now in a position to know the order of the normalizer of sigma. This, however, we won't do today. We will see it in the next group theory video, and there itself actually the section will properly end, and after that we of course have our exercises that we will start solving. So that's just it for tonight. Our next upload is this coming Friday, and on Friday, what shall we do on Friday? On Friday, let us go back to field theory, because there we have completed the proof of that main theorem, and we are eager to see what its consequences are. We have been saying for quite a long time that this will give us the condition that will allow us to say which real numbers are constructible. So on Friday, let's see what those conditions are, and using them what else we can say. So that's just it. So see you on Friday. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.